Dear student, welcome to EPG Pathshala. Today my talk is on the module Interaction of Pollutants with Soil Component Part First. As we all know that soil pollution, it refers to the change in the primary structure of the soil due to the invasion of outside contaminants. Now this process has led the researchers to research on this area, and now the studies are being carried out on the process of soil interaction with the components. Further studies are being carried out on the study of soil engineering structures, soil microstructures, etc. Now in all this process, the structure and mineralogy of soil plays a very important role to understand the mechanism of the interaction of pollutants with the soil. Although whole of the process is a very complex process to study, but we will try to take various factors independently while going through the module. Let's study in the detail process involved in soil pollutant interaction. First, we are taking acid-base equilibrium process. The array of proton transfer reaction governs the acid-base equilibrium process. If this case is considered proton donor in an acid and base is the acceptor. For example, if soil solution is being considered as an aqueous system, water is always the present acceptor. For example, during the dissociation of an acid in the soil solution, one of the dissociation product will be hydronium ion, and the acid strength of the hydrogen acid relative to the hydronium ion will be a quantitative parameter. In a dilute solution, the activity of the hydrated protons equals that of hydronium and ion, and the pH value represents the hydrogen ion activity. Under these conditions, substituting for pH into the following equation has been given in the following equation. Next process will take precipitation and dissolution. In soil medium, this is a chemically occurring heterogeneous reaction. Under various physicochemical conditions, a process of dissolution and precipitation of minerals in water occurs. This reaction plays a major role in the natural system, while a lesser one in the fate of pollutants. However, the dissolution of a particular chemical in the soil water phase could alter the speciation of water phase pollutant. Equilibrium constant can be considered to estimate the vicinity of dissolution or precipitation reactions of the system. As the dissolution ends only when water saturation occurs, supersaturation is the stage where precipitation of chemicals occurs. In case of soil medium, a heterogeneous chemical reaction, that is dissolution reaction, occurs, and the solubility in terms of a solubility product with equilibrium constant is characterized to predict the solubility and the ways in which the solubility is affected by the solution variables. A chemical substance can be present in one or more crystalline form, but excluding a transition temperature, considering chemical composition of the system, just one form is thermodynamically stable. However, the stable forms are less soluble than the metastable one. Similarly, the allotropic forms have different activities, the highest being with the most unstable one. Co-precipitation of inorganic trace elements, for example, as contaminants in their oxide forms, may blend the solubility product assessed by producing ill-defined stoichiometric solid solution. So, for deducing the changes in solubility in terms of solubility product, the estimation of solubility product in affiliation to equilibrium constant is necessary. Now, the figure 32.2 shows the schematic solubility diagram relationship between solubility and saturation. Next process is the ligand effect. The ligand is defined as a coordination compound formed by a central atom of cation and molecules of anions. In this, a complex formation takes place by combination of cation possessing molecule or anions possessing free pairs of electrons. The complex can either be electrostatic, covalent, or a mixture of both. The central atom is cation and anions being ligand in which the molecules form coordination compound. The molecules forms a complex called chelates consisting of more than one ligand. So, Conceptually, the complex formation is in coordination with the acid base and precipitation dissolution reactions. After reaching the soil solution, the base ion initiates a continuing search for its partner. The cations undergo exchange reaction by following coordination reaction, in which exchange occur between the soil solution with the coordinated water molecules and prefer the ligands. A complex called an inner sphere complex is thus formed between a Lewis acid and base, while an outer sphere complex is formed when the acid and the base molecules are interposed by the water molecule. The hard Lewis acid has high electronegativity, small size, low polarizability, high oxidation state, and whereas a molecular unit with low oxidation, large size, low electronegativity and high polarizability is the case of a soft Lewis acid. A hard Lewis base has a high electronegativity and a low polarizability, while a soft Lewis base displays low electronegativity and high polarizability. Next is oxidation and reduction equilibrium process. These reactions involve transfer of electron from donor to the acceptors. A redox reaction consists of two half reaction, a reduction and an oxidation. Oxidation number is the concept used to designate a reduced and oxidized chemical species. A hypothetical valency to every atom is assigned. Every redox reaction includes two half reactions, a reduction half reaction and an oxidation half reaction. A reduction half reaction, for example, includes acceptance of electrons by a chemical species, while an oxidation reaction has donor chemical species. In the given reaction, here A denotes a chemical species in any phase and the subscripts OX and red denotes the reduced and oxidized states respectively. Other parameters such as A, B and N are the stoichiometric coefficients. Though the potential in soil solution always exists for redox reactions to occur, it is not necessary that the proficiency of the reaction also occurs. If the redox reaction is favored thermodynamically, it is not necessarily that it is favored kinetically also. Under these conditions and in the presence of a catalysis process, as the reactions are slow, the equilibrium could be achieved. In case of redox reactions in soil medium, the microbial organisms may act as catalysts, play an effective role under favorable conditions. The redox reaction can only be controlled by thermodynamic processes, while reaction kinetic controls the soil microbial induced catalysis. Next is the effect of mixed solvent and surfactants. Dispersing agents or surfactants are responsible for penetration of the potentially toxic organic chemicals in soil, either in mixture of solvent or in other forms. The major effect is an increase in solubility of the solvent. Most of the organic chemicals that are potentially toxic reach the soil either as a mixture of solvent or in formulation with dispersing agents that are surfactants. In a solvent such as water, these formulations increase the solubility of the active compounds. In a solvent which forms a nearly optimum solution with another, limiting the solubility of a third substance and a lower crystal stability value, the logarithm of its solubility and the mole fraction composition of the solvent are nearly in a linear function. In case of a solvent pair where the solubilities of the third substance vary greatly, these solvents due to their varying solvent powers are typically much less soluble in one another and form miscible solution which are non-linear. Thus, the amount expected to be dissolved by the more powerful solvent is much larger as compared to quantity of solute dissolved in a mixture of two equal amount of the solvents. When a case of powerful organic solvent miscible with water is considered, a more linear slope for the log solubility versus solvent composition relationship can be derived when the composition plotted as volume fraction instead of a mole fraction. Next is the effect of temperature on solubility. The solubility of most inorganic and organic pollutant in water is in direct proportional relation with temperature. The temperature along with seasonal variation directly as well as indirectly affect the solubility of contaminant in the soil aqueous phase. Also, the seasonal variation in temperature could affect the toxic chemical solubility in the soil. So, at a given time and ambient temperature, the recognized solubility equilibria defines only the solubility of the compound. An exceptionally complex and heterogeneous structures defines a soil environment. This soil environment supports plants and animal life by developing a particle pore matrix consisting of solid, liquid and gas phases. This is necessary for an effective cycling and storing of nutrients. Also, the migration of pollutants is influenced by many other factors as well as the complexity of situation. As the heavy metals penetrate in the soil, ionic composition and concentration changes in the medium that disrupt the equilibrium state of the soil and cations in the adsorption layer. After this, in the free medium, the cations displace the one present in adsorption layer, making the soil attain a stable state. Simultaneously, due to the developed electrostatic force, the cation invade the heavy metal that are absorbed by the surface of soil particles and get neutralized by the anion in the adsorption layer. With a gradual increase in concentration of invading cations, more anions become neutralized, leading to reduction in electrokinetic potential, resulting in diffusion of the double electric layer. In addition, other reactions by heavy metals like complexations reactions, replacement reactions, redox reactions, etc. with cement particles generates soft organic plastid, causing rupture of the interparticle aggregations. The physical, chemical and biological processes influence the behavior and interaction of pollutants with soil in all the three components: solid, liquid and gas. The physical processes include transport and retention and mainly defined by physical parameters of the medium. While in case of chemical processes, they rely largely on type and chemical nature of pollutants. However, biologically controlled processes include the biotransformation and biodegradation process depending on their microbial ecology, depth and the oxygen ability at the pollution site. As the pollutant encounters the soil grains, may retain on the surface of grain by adsorption or accumulate in the intergranular space, forming concentration that retain their original chemical composition or forms elements that have been altered due to chemical reactions. The contaminants enters a natural environment resulting in instability, disorder or harm to the ecosystem, that is physical or biological system. These elements of pollution can be alien or foreign substances, energies or naturally occurring contaminants. Pollutant migration has noticeably impact on engineering aspect of the soil, so is being taken up to study by the environmental geotechnical scholars. The interaction mechanism of soil pollutants consists of various biological, physical and chemical processes functioning in all three phases of the solid venues. They generally include three main groups of processes: confinement on and in soil body, soil solution movement and diffusion, chemical transformation within the soil. The transport and confinement of soil and pollutant components are the major physical processes which has been shown in the figure. They mainly rely on the physical variables of the soil medium, that is temperature, size, charge, etc. On the other hand, chemical procedures are defined mainly on the type and chemical nature of pollutants, while biologically controlled processes majorly depends on microbiological, biotransformation and biodegradation process depending on microbial species, depth of their occurrence and the amount of oxygen available at the site of pollution. Next is the fate of the contaminants. The fate of contaminants in soil follows either through point source or diffuse pollution. The main difference existing in between the two lies the transferring mechanism of contaminants to the soil. Point sources such as landfills and incinerators etc. use soil as a support and are linked to the events that necessarily transport pollutants into the soil. The diffusion sources are linked with natural phenomena including long range transport, sedimentation, recycling, inadequate waste treatment and agricultural practices. Generally, the most hazardous contaminant in soil are persistent organic pollutants, inorganic pollutants and heavy metals. Persistent organic pollutants are derived anthropic and characterized by high lipid affinity, semi-volatility and resistance to decomposition. If the heavy metals cannot be degraded, their presence in the soil could be due to certain natural processes like the soil formation or due to anthropogenic activities. Some of the important essential elements when present in ideal condition are suitable like copper, iron, manganese, zinc, cobalt, while others like mercury, lead, cadmium, they are potentially toxic elements. The bioavailability of a pollutant is decided by soil and on-site characteristics. The bioavailable portion is known to affect the plants, animals or human directly as it is taken up by their bodies. The site conditions affect then contaminant binding to the soil particles and its solubility in water. Higher solubility generally means that more bioavailable of the contaminant, but it also relates the contaminant likeness to leach out of the soil. As the contaminants penetrates in soil, the contaminants undergo chemical changes and degrade into products that may have more or less toxicity in comparison to original compounds. The different contaminants differ in their tendency to leach. Through leaching, they end up in soil water or in groundwater, volatilize into the air, bind tightly to the soil. The soil characteristics that may also affect the fate of contaminants. Characteristics that may affect the behavior of contaminants include soil mineralogy and soil texture, pH of the soil, organic matter of soil, moisture content, temperature existing in the soil and the presence of other chemicals in the soil. Nature and behavior of inorganic contaminants. Heavy metals are one such group of numerous classes of substances if they reach the critical level considering the human health, soil fertility and ecological risk, food safety. These metals being the common contaminants in the soil can bioaccumulate in the organism and thus their absorption by the organism increase with time in comparison to the level evaluated in the environment. This is due to the higher absorption rate than the excretion rate of the organism. Also, the allocation of heavy metals amongst the solid phase and soil solution is deemed to be the main factor to assess the environmental outcome of the heavy metal accumulation in the soil. An analysis of soil profile along with the physical and chemical analysis is essential for assessing if soil is a barrier against the inorganic contaminant, especially heavy metals. In the solid phase, retention of heavy metals in soil is dependent mainly on pH, linked to clay minerals, hydroxide, humic substances, iron oxides and manganese present in the soil that control the attenuation effect on anionic forms as well. The processes involved in retention and release of heavy metals involve precipitation, decomposition, ion exchange, adsorption and desorption. The precipitation reactions may involve release of discrete solid phases that are adsorbed by the soil surfaces, while the ion exchange reactions are related to exchange between an ionic species present in the soil medium and an ionic species retained at site possessing a permanent charge on the soil surface. The process of absorption and desorption can influence all ionic or molecular species and generally affect the adsorbent site with the pH dependent charge like iron, hydroxide, aluminum, manganese oxide, humic substance and clay minerals. So, in this module we have learned that how the soil is being polluted by the various activities of human and the site and the amount matters a lot, whereas not all the pollutants are biologically available. Mainly it depends upon the solubility of the pollutant, that is more the pollutant is soluble, more it is biological available. Further, in this module we have also seen the various soil processes, the interaction between the soil and the pollutant and the fate of the contaminants has also been studied in this module. Thank you.